Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Multi-component distillation, column sequencing and selecting the optimized column sequence. In this video course, you will learn to determine the number of columns for a multi-component feed mixer, to determine the number of possible sequences, how to select the optimized column sequence, an example to strengthen your understanding. Please subscribe to the channel. By subscribing, you will motivate us to produce knowledgeable video content for you. So subscribe now before you forget. In refineries and petrochemical plants, the feed to the distillation column contains more than two components. Designing a single distillation column to separate these products, though possible, presents engineering challenges and is a complex exercise. The more common approach to separate multi-component feed streams is to use a sequence of columns, with each column producing two product streams with one condenser at the top and one reboiler at the bottom. For a binary mixer consisting of two components, A and B, the separation into near pure products can be achieved in one column. If A is the light component and B is the heavy component, the ease with which A and B can be separated depends on the volatility of A or volatility of B. The volatility of A is defined as a partial percent PA divided by XA, the mole fraction of A in the liquid mixer. In the same way, volatility of B is defined. The relative volatility alpha is the volatility of A divided by the volatility of B. By specifying composition of A in the distillate and bottom, the composition of B in the distillate and bottom gets fixed, and the column can be designed for a specified recovery. Since the multi-component system has more than two components, the above approach used in binary distillation cannot be used in the multi-component distillation. To determine the relative volatility, it is required to identify two components that can be separated to the desired specification to the extent possible. The components thus identified with specified fractional recoveries are called key components. The most volatile of keys are called light key, LK, and the least volatile is called the heavy key, HK. The light non-keys are the components which are more volatile than the LK, and the heavy non-keys are the less volatile than the HK. This step of identifying the LK and HK with specifying their recoveries in the distillate and bottom is an important step in the analysis of multi-component distillation system. With this understanding, let me move on to determining the number of columns required for a multi-component feed mixer and how to select the optimum sequence. For a multi-component system consisting of n components, n-1 columns are required. An important process design problem in multi-component separation is the separation sequencing. Column sequencing is concerned with the selection of the optimal method and sequence for the separation. This discussion on sequencing of distillation is restricted to ideal feed mixtures such as hydrocarbon mixers where the separation is achieved by conventional simple distillation columns. The approach to determining the optimal sequence involves arranging the components in the mixer to be separated in some ranked list of appropriate physical or chemical properties such as relative volatility. In general, there are two methods. 1. Direct sequence. 2. Indirect sequence. Number of sequencing methods possible for a three-component system consisting of A, B and C are 2. as shown in this figure. In the scheme 1, the lightest component A is taken as overhead in the first column C1. The bottoms of the first column BC is fed to the column C2 and the lighter components B is removed as overhead. So in both the columns, the lighter components are removed as overhead. This scheme is called direct sequence. In the scheme 2, the heaviest component C is first removed as bottom product in the column C1 and the lighter components A and B are removed as overhead and fed to the column C2, where again the heavier component B is separated as a bottom product and the lighter component A is removed as overhead. Note, this scheme takes the heaviest component as bottom product in each column. This scheme is called the indirect sequence. The major problem with the column sequencing is the large number of possible sequences, which grows exponentially with the number of products. The number of possible sequences for a desired number of products is given by the formula ns equal to 2 times p minus 1 factorial divided by p factorial into p minus 1 factorial, where p is the number of components, ns is the number of sequences of ordinary or simple distillation columns. Let us now consider a 4-component mixer containing A, B, C and D that is to be separated into individual products. The number of columns required in the conventional distillation method are 3. The possible column sequencing using the above formula are n is equal to 2 times 4 minus 1 factorial divided by 4 factorial into 4 minus 1 factorial, which works out to 5. It is the number of sequences of conventional distillation columns required are 5. The 3 columns and the 5 sequencing schemes are shown in this diagram. In the scheme 1, the lightest component A is taken as overhead in the column C1. The bottom of the first column BCD is fed to the column C2 and the lighter component B is removed as overhead. The bottom CD of the column C2 is fed to the column C3 and the lighter component C is removed as overhead and the heavier component D as the bottom. Similarly, there are 4 other sequences where the 3 columns remove the 4 components one by one as pure products. The 5 schemes are separately shown in the box type diagram for better understanding. The scheme 1 is a direct sequence and the scheme 5 is the indirect sequence. The number of sequences grows as the number of components as final product increases. The analysis to determine the most optimal scheme becomes rather complex. In many instances, the vapor flow through the system is a good indicator of process economics since it directly impacts both the capital and operating costs of the equipment. Lower vapor flows result in smaller columns and possibly lower utility usage. Column sequence alternatives evaluated using total annualized cost TAC will reflect the actual process economics more closely than those evaluated using vapor flow rates. To calculate the total annualized cost of each scheme, the process engineer has to calculate the vapor flow rates first. Hence, total annualized costs are more time consuming and laborious to calculate than vapor flow rates. The optimized selection procedure for the above discussed 4-component system is commenced by taking one sequence at a time and estimating the vapor flow rate for each of the 3 distillation columns C1, C2 and C3, considering near pure products. The vapor flow rate from each column in the selected sequence is added to obtain the total vapor flow rate. The same procedure is repeated for all the 5 sequences and the total vapor flow rate estimated. One with the least total vapor load is the optimized sequence and is preferred for final design. Approaches to sequence selection, heuristics. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. The heuristics are based on observations made in many problems and attempt to generalize the observations. The 4 commonly applied heuristics are presented next that can be used as guidelines in column sequencing. Heuristic 1. Separations where the relative volatility of the key components is close to unity or that exhibit azeotropic behavior should be performed in the absence of non-key components. In other words, does the most difficult separation lost. Heuristic 2. Sequences that remove the lightest components alone one by one in column overheads should be favored. In other words, favor the direct sequence. Heuristic 3. A component having a large fraction of the feed should be removed first. Heuristic 4. Favor splits in which the molar flow between top and bottom products in individual columns is as nearly equal as possible. Distillation column sequencing. An example. Problem statement. A constant relative volatility ABC mixer is to be separated into nearly pure components. The relative volatilities are in the ratio of alpha A is to alpha B is to alpha C equal to 8 is to 2 is to 1. The feed mixer is ideal and the molar rate of the feed mixer is A equal to 0.5 mole per hour, B equal to 0.35 mole per hour and C equal to 0.15 mole per hour. The feed is a saturated liquid. Separation by conventional distillation needs 2 columns to separate this feed into nearly pure components. Find out the optimal column sequence. The solution. Selection of light key and heavy key in each column is an important decision to be made right in the beginning. Based on the values of the relative volatilities of the components, their selection is made as follows. The relative volatilities of components A, B and C are given as shown in the table below. It is apparent that in the feed mixer, A is the lightest and C is the heaviest. For separation of the 3 components, 2 columns are needed and 3 sequences are possible. In scheme 1, for column C1, A is LK, B is HK and C is HNK. For the column C2, the component B is LK and C is HK. In scheme 2, for column C1, the component B is LK, C is HK and A is L and K. For column C2, the component A is LK and B is HK. Shown in this figure are the 2 schemes, scheme 1 and scheme 2. Scheme 1 is a direct sequence and scheme 2 is an indirect sequence. Feed, distillate and bottom product flow rates for the 2 columns for each of the two sequences are as depicted. It is assumed that all the three products are near pure products. The calculated column-wise vapor flow rate for each of the two schemes is presented in this table. The minimum reflux is estimated using Underwood equation from which vapor flow rates are computed. For scheme 1, vapor flow in the column 1 is 0.856 mole per hour, and that in the column C2 it is 0.951 moles per hour. The total vapor flow rate for the scheme 1 is 1.807 mole per hour. For the scheme 2, the vapor flow in the column C1 is 1.47 mole per hour, and that in the column C2 is 0.841 mole per hour. The total vapor flow rate for the scheme 2 is 2.311 mole per hour. Thus you can observe the scheme 1 has less total vapor flow rate than scheme 2. Hence, scheme 1 is the preferred sequence for final design. It is a reboiler that generates a vapor, that is boil up. Hence, vapor rate determines the reboiler duty and the size of the reboiler. The column diameter is decided by the vapor flow rate through the column. Thus, the total annual cost TAC, which is proportional to heat duty and column sizes for scheme 1, will be lower in this case. Hence, the scheme 1 is preferred column sequence for the given separation problem. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.